All right, hi, I'm Sammy, and now that you know what Featran is, I'm going to be talking about an application of it and using it in practice. And pictured below are some of the people on Homer that I've been working with, Carl, James, Oog, Ben, and Tiffany. Okay, so again, now that you know what Featran is, I'm going to be talking about an application of it. And so the goal is for you to understand how to use Featran for model training and also in a service that evaluates the model. And in order to accomplish that, I'm going to take you step by step through conception to deployment for an ML-inspired use case at Spotify. So I'm using the word inspired because I'm not going to go into all of the details of working on it. So basically cutting out some of the extra stuff in order to make Featran the main focus of the talk and to let it be the true star of this presentation. A tentative outline for what I'll be going over is first, defining the problem. Next, talking about an ML solution for the problem. Going into feature and model selection. And finally, into the infrastructure that we are building and have built to accomplish this. Okay, so starting off with the use case and ML solution. So from the introduction, I work on a team called Homer. And based off of that name, you might be able to tell that we work on the homepage for Spotify. And the use case is that we want to order content on Home. And so currently, Home is structured in the following way. We have a shelf, which is characterized by its name, such as you see here, it's made for you and you might also like, along with a collection of media items. And so a media item is defined by its URI. And that's basically a link that you can click on that will allow you to listen to something. So this could either be like your own playlist, a Spotify playlist, an artist, or an album. And so the goal that we were given is, given a shelf, order the media items in order to maximize for total consumption time. So basically we want to put the more popular items at the front of the shelf in order to maximize for total consumption streams. Okay. So given this goal, an ML solution to this problem could be the following. So first, we would train a classifier to predict the probability that a media item and shelf pair will be played. And then, given that probability, we can order the media items in terms of that. So based off this approach, we had to make two decisions. First off is model selection. That is, how are we going to even choose a model to model the probability of a stream given an input feature? And then secondly, the feature selection, which is given a model, what are the most informative input features? And since this is a talk about Featran, I'm only going to be focusing on the feature selection components. So that's basically asking, like, what is this X that you see? All right. So at the very bare minimum, the number of, or the features that we're going to need at least are going to be the shelf name and the card URI, or media item URI. But we'd also like to add in some additional contextual information, such as weekday, time of day, user location, user attributes, or media item type. And so on the right-hand side, this is going to be our basis of our input features. All right, so we're going to have our raw input features, and then we want to go to our model input features. So basically taking those either categorical representations and converting it into some form X that can be passed into a model. And so this is where Featran comes into play. And so you can think of X as, something like this, basically a dense vector full of zeros and ones. Okay, but before we started even using Featran, we first asked ourselves the question of, should we even be doing this? After going into our ML formulation, we kind of had an idea of what the model and the input features should be, but we weren't sure that it was actually going to work. So what we initially did was we collected a small subsample of user data from Home, where we had our raw inputs, which from the other slide were examples were like the shelf name, the media item URI, and some additional contextual information, as well as the raw labels, which would be, for example, how long a user listened to a media item. And so we initially experimented with model and feature selection in Python using SciPy and sklearn. And that allowed us to kind of really quickly and initially test a lot of different ideas. But once we narrowed them down and we were confident that our approach would actually work, then we got to the phase where we said, let's start actually building it. And that leads to the next section entitled Building Stuff. And so this is the end architecture that we created, but let's first concentrate on just these three components. The first being the common featurization library, which held our Featran aspect of it, as well as common pre-processing steps. And that's going to feed in both into a data pipeline and a shelf reordering service. So let's first concentrate on the common featurization library. Okay, so the purpose of the common featurization library is to take our raw data and convert it into an intermediate form that can then be extracted by Featran. So to make this more concrete, let's give this an example. So our raw data is going to have information such as the time played, the media item URI, the shelf name, and a timestamp. And then from there, our intermediate form is going to be called process data, which is also going to have the time played. And then from the media item URI, we're going to get two other features, which is the media item ID, which we use because for media items such as daily mix, it's going to have a unique URI for each individual user. So it's not going to be particularly informative if we want to train a model in order to predict if you like daily mix. So we're going to first transform that across all users to map to a common ID. And then also the media item set type. So this could be like a personalized playlist, which is what daily mix is, a Spotify playlist, or your playlist. We'll also have the shelf name, and then from the timestamp, we're going to extract the weekday. So the process data is really just meant to convey that we're going to do data pre-processing, and all this data pre-processing is going to take place in the common featurization library. And then the actual extraction step, that's going to occur with either in the pipeline or the service. So then the first case is we want to take that raw data and make it something that we can actually work with. And so our common featurization library is written in Scala, so we're just going to make a raw data case class that holds these features. And similarly with the intermediate representation, we're just going to make another case class called process data that has all the features that happen after we do the pre-processing on the data. And so the common featurization library, it's also going to hold two other functionalities. One is the feature spec that Fallon talked about. So this works out pretty well that the two transformers that I'm using in this example are binarizer and one hot encoder. So we're going to create the label using the binarizer. And so we're going to say if someone has listened to this song for more than 60 seconds, let's set the label to 1, indicating that they like this, they enjoyed that experience, and 0 otherwise to create like a negative example. And then we're going to use a 1 hot encoding for the media item ID, set type, shelf name, and weekday. And then this home featurizer object, that's going to contain the feature specification that we defined above, as well as just the function that goes from the raw data to the process data. And again, that's just meant to convey that all these pre-processing steps are taking place in this common featurization library. All right, so the next step after we had this was building the data pipeline. So let's take a look at that. At Spotify, we write data pipelines using Shio, which some of you should know about. And so the two inputs to the data pipeline is one, it's going to use that common featurization library, as well as like home logs. So let's look at the steps that are going to take place in this data pipeline. So first is simply just reading in the historical log data. The second one is we're going to get the raw data and convert it to a process data. And so the steps in this process would be, one, using the case class raw data that we defined in our common featurization library and just extracting all the fields that we need from our input data. Then calling the process data function, again defined in the common featurization library. And then finally, we're going to have a S collection of process data. And so the next step is just extracting the data using the home featurization specification. And after that, get the feature values, and in our case, we wanted it to be a sparse double. So only a few steps that you need to do before you can get the data in a form that you want. And then the final steps is just saving the training data along with the Featran settings. So in our case, we wanted to convert the sparse vector to a format that could be easily read during our model training, which was to just save it as a string. And then also, we'll save the training data, of course. And then finally, save the Featran settings. Because in the end, we're going to want to recreate these vectors using the same process within the service. OK, so after the data pipeline is run, we have two outputs, one being the Featran settings, and then also the training data. And then so although I'm not talking about this, the next steps would be actually doing the model training, and then afterwards you're going to have a trained model. So this would be your H that you saw in the previous slides, and you would get then the optimal weights associated with it. And so finally, that brings us to the shelf reordering service, which is also going to be using this common featurization library. And the two inputs that it requires are the Featran settings as well as the trained model. OK, so let's take a look at the shelf reordering service. So just a side note before I go into the details is that at Spotify, our microservices are written in Java using Apollo, which is an open source library, and that we also generally use protobuf to send messages to the service. So in our case, we want the messages to have the media item URI along with the shelf name. And then we can think of a home request as having just a bunch of this information. And so that's going to be the input to the reordering service. All right, so let's take a closer look of the Featran components within this shelf reordering service. So similarly as what was done in the data pipeline, we have to get our data from somewhere, what we actually need to score. In this case, it's coming from the request and the protobuf. And then finally, doing a very similar functionality is that we get the raw data and we convert it to the process data. So again, we're using this case class raw data that was defined in our common featurization library. The only important note here is that we're using a dummy label, since in the data pipeline, we were using historical logs. So we had information about how long a user actually listened to a song. Whereas for here, we want to going into the prediction phase and want to guess how long a user is going to listen to this song. So for now, we're just inserting a dummy label. We're calling the same function, again, defined in the common featurization library, called process data. And in the end, we output a list of process data. OK, so then the next steps is we're going to get a Java-friendly version of the feature spec. I keep on saying that, which is, again, defined in the common featurization library. We're going to load the Featran settings. And again, we get these Featran settings after running the data pipeline and saving the Featran settings, and then calling the extract method. Except in this case, we're calling extract with settings, and we're passing in the Featran settings. And finally, we're going to output our values using a sparse double. So one important note is I mentioned that we're using a dummy label, and so to then actually use the features for the purpose of prediction, we're going to strip out the entry that corresponds to a label. And this basically involves just like a shift by 1 over. It's just important that you remember to do it, or else all your features are going to be off by 1. So this is a little detail that I bring up. You probably would imagine because we did it wrong the first time, so just make a mental note for anyone else who plans on doing this in the future. All right, so what happens next after we run Featran is we go from a sparse double to another form that can be passed into a model, get the model scores, return the home content with the scores, and then reorder home content using the scores. So I want to now look at the SHIO data pipeline and the Apollo service side by side, just so you can see how common the functionality of using Featran is in both of these settings. One, which is, again, SHIO data pipeline and an Apollo service written in Java. OK. So both, initially, they have to get their data from somewhere. The SHIO pipeline reads in historical logs, whereas the Apollo service gets its message from like a user request that actually sends in the home content. From there, we're again using this raw data case class that we defined in our common featurization library, calling the same method called process data, again defined in the common featurization library. And in the end, we either get an S collection of the raw data or a list of the raw data. In the Java service, there are 2 additional steps that you have to take. One is getting this Featran-friendly version of the specification. And then also, you have to get your Featran settings, which were saved during the SHIO data pipeline. And then you're also calling extract in a very similar way. The only difference is in the Apollo service, you're calling extract with settings, and you're passing in the Featran settings, which Fallon showed you what they look like. It's just a string that has all of the aggregations that were saved. And then finally, depending on the final form that you want to use, you get your feature values as either it could be like a dense array or a sparse array. And then finally, in just the SHIO data pipeline, the important part there is we always need to save the Featran settings. And so again, to really drive how similar this is, let's go through this exercise one more time, but have them swapped and also upside down. But all right. No, I'm not actually going to do that. It's getting late. You're all here. But the point I would make is if I did do that, you might be able to follow along, because Featran is very easy to use within a service and also a pipeline. OK, so again, let's just go through this architecture one more time. So we started off with defining that common featurization library that made it really easy to use Featran in both a SHIO data pipeline and a Java Apollo service. From there, we ran our data pipeline on historical home logs. We got from that both the Featran settings and the training data. From there, we're able to run our model training algorithm. And the output of that would be the train model. Both the Featran settings and the train model are the inputs into the shelf reordering service. And from there, as like a user, we're able to query to get model scores. OK, so hopefully at this point, you have known that, or know that Featran is both pretty easy to use for both model training and within a service that evaluates the model. And so what we did was we started with the problem. And for that, it was reordering content on home so that the more popular items would be placed in a more viewable position. We then talked about how we could use machine learning to formulate the problem. From there, we decided to first validate the hypothesis by using a small subsample of home data and initially prototyping in Python using sklearn and scipy. And then once we were confident that this was a viable solution, we moved on and basically developed the system architecture, which had 4 main components, being the common featurization library, the data pipeline, the model training, and the service. All right, so thank you for listening, and questions? All right, perfect. Yeah. Brad?
What will happen if you have to change something in your future, your common future library? Which step would you have to do again, and how would you
So it depends what we change. If we if we change the feature specification, then we'd have to rerun the data pipeline as well as the model training. So every time, or even if the data that we're using to train our model changes as well, we'd have to rerun everything again. All right, well, thank you for listening.